Okay, greetings everyone, and welcome back to our series of online lectures for CHE 2300. Yesterday I uploaded a video for lecture notes 18 to YouTube. Unfortunately, in doing so, I inadvertently skipped over lecture note 17. So in today's video, we will be going over lecture note 17 regarding or related to fluidized beds. Before we start on that lecture, though, I do want to go back to our packed beds lecture, which is the last lecture that we had when we had an in-person class, and talk about a couple things that I didn't get to discuss with packed beds, and then transition from that into fluidized beds. Okay, at the end of our packed beds lecture, you were introduced to the Ergun Equation. And I told you at the time that I highly recommend that you use the Ergun Equation when solving problems involving packed beds, because the Ergun Equation applies for fluid flow for any particle Reynolds number. The equations above, these two equations here, they are for specific flow scenarios. One is for our low flow or Stokes flow, and the other is for much higher particle Reynolds numbers. And so, again, in order to use either one of those equations, you have to make a choice or a calculation based on the particle Reynolds number. If you go with the Ergun Equation, the particle Reynolds number is irrelevant, because the Ergun Equation applies to all particle Reynolds numbers for packed beds. Specifically, the Ergun Equation allows us to calculate or relate the pressure drop over some length or height of our packed bed as a function of both the packing material and the fluid itself. So it's a function of things like the sphericity and diameter of the particle, the void fraction of the packed bed, as well as the density, viscosity, and superficial velocity of our fluid. Again, superficial velocity is the velocity of the fluid as if there were no packing material inside the column. That is to say, the volumetric flow rate of your fluid divided by the cross-sectional area of the column. That will give you your superficial velocity. So I'm going to say this one more time, hopefully to stress this point, but I highly suggest that you use or utilize the Ergun Equation when solving problems for packed beds. The one major thing I did not discuss when we went over packed beds, two major things are: one, the actual packing material itself, and then two, when I might want to use a packed bed over some other type of column, such as a plate column. So, what you have here is a schematic of a packed bed column. And in terms of our packing material, there are a number of other things on this figure. We'll get into some of those in a bit more detail when we get into fluidized beds here shortly. But the one thing I want to highlight here is that our packing material falls under one of two categories. Our packing material can either be what is known as structured packings. This is packing with a regular geometry. And this type of packing is designed with a specific size, shape, and void fraction, and is typically either bundled together or is a solid piece of metal. Again, this is what's known as structured packing, and it's called structured packing because it is intentionally designed to lay inside the column in a particular manner and therefore have a particular void fraction that is consistent based on the type of structured packing that you choose. More often, or I should say oftentimes, you run into the other category of packing material, and that is what is known as random packings. Our random packings are simply pieces of some material, whether it's a ceramic or a metal, and these little pieces are dumped inside the column, and in doing so, they form a random packed bed. Meaning that if I pull those particles out of the column, and then I if I pull that packing out of the column, and then I dump it back into the column, there's no guarantee that I will end up with the same void fraction as I did in the first scenario. And that is the case because, again, this is referred to as random packing because the packing randomly packs itself inside the column. When it's dumped into the column, if it becomes fluidized and then resettles, it will more than likely resettle to a different void fraction than it was originally. Our random packing, the big thing I want to point out with random packing is the packing material that you see here. This packing material is what is known as a Raschig ring. These Raschig rings are typically made of ceramic. They can be made of metal, and they are hollow, cylindrical pieces of material or packing that, again, are simply dumped into the column, and they form a random structure based on how they have settled in the column. I can change the geometry, the shape, the openings of my different types of packing depending on what type of void fraction, flow rate, pressure drop that I'm trying to achieve across my packed bed. But I do want you to be familiar or have been introduced with the term of Raschig rings because you will run into those when you get into your 407 lab and I believe are doing sulfur dioxide extraction, but don't quote me on that. Okay, so why would I want to choose to use a packed bed column, or why might I choose not to use a packed bed column? So our packed bed columns, they are not ideal for very low liquid flow rates. They are ideal for foaming systems as well as corrosive systems. And typically, if I have a packed bed column, all right, if I, what am I saying here? Okay, so for packed bed columns, they are most ideal or should be considered. So let's write that, should be considered for columns with diameters less than about 0.6 meters. So somewhere on the order of 1 to 2 feet. If we're in that range in terms of the diameter of our column, then having a packed bed column is probably going to be the more ideal scenario. What else do I want to say? So while we're sitting here, I want to point out, I'm not sure if I did, ultimately what the purpose of these different packings is. And the main function of these different packings is to produce a large surface area, right, or large interfacial area between the gas and the liquid in my system. Right, so if I imagine the scenario where I am scrubbing sulfur dioxide from air, I have my water that flows in through the top of my column, and instead of it falling and just forming some tall column of liquid, I have it flow through a packed bed that distributes that water. It increases the interfacial area between the water and the dirty air that is flowing upwards through the column. An increase in that area ultimately results in an increase in mass transfer of my system, and that is, of course, the ideal scenario. Okay, I believe that is all I want to say about packed beds at this time. And so with that, we will transition into fluidized beds. Let me get my eraser out. I've already filled in some of this stuff. Sorry about this. I'm going to leave those. That's fine. Let me get rid of these. Get rid of this. Oop. Slow down. Okay. I believe I have gotten rid of it. Yep. Okay. So, let's now talk about fluidization or fluidized beds. The scenario I want you to imagine is that I have a packed bed column, i.e. I have a column that is full of some particular packing material. I begin to flow a fluid upwards through the column from the bottom through my packed bed, and I slowly increase the velocity or flow rate of that fluid. At some point, once I increase the velocity of my fluid to a high enough value, what happens is that my packed bed starts to become fluidized, meaning that it starts to act less like a collection of stationary solid particles and begins to act like a fluid in my system. So in this simple schematic, what I have is I have my fluidized bed. Right, that fluidized bed is sitting on top of a distributor or a distribution plate. And then the area below that distribution plate before I actually enter my packed bed is what is known as the wind box. I just want to point that out. Let me talk a little bit more about that distribution or distributor plate. That distributor serves essentially two main functions and then a small sub-function of one of those. So the first function of my distribution plate the function, it makes sense, is to distribute the fluid uniformly. That makes sense. It's called a distribution plate. Therefore, its main function should have to do something with distributing. So the idea behind this is I have some fluid that's moving through my column. Right, before it hits my distribution plate, right, I'm not necessarily directing the velocity of that fluid in any particular direction. My distribution plate allows me to more uniformly spread that velocity out as it begins to enter my packed bed. So function 1, distribute fluid uniformly. Function 2 is to prevent or minimize backflow of particles. As my bed becomes fluidized, those particles begin circulating above that distribution plate. And if I didn't have that distribution plate there, there's a chance that my particles could fall to the bottom of my column or have backflow of those particles. What I'm going to call a subfunction of the distribution plate, because it's under the same or in the same vein as the function I just wrote, is that the distribution plate supports the weight of the solid particles when flow is stopped. When flow is stopped. I can't run my column 24 hours a day, 365 days a year. There are going to be periods of shutdown. I'm going to need to maybe replenish some of those packing materials inside my column. I may need to clean the column itself. I may need to replace some type of part of my column. So there are going to be periods of shutdown. There are going to be periods of time where I am going to have no fluid flowing through my column. If I didn't have this distribution plate, all of my particles would simply fall out the bottom of my column. So it also serves the function of supporting the weight of those particles when fluid flow is stopped entirely. What you see here at the bottom of the page are what I would call two extreme ends of the spectrum. On the left-hand side, you have a packed bed column where the diameter of the column is very large in comparison to the height of the packed bed. On the right-hand side, what you have is a column that has a relatively small diameter in comparison to the height of the column, the height of the packed bed. On the left-hand side, what we run into is we run into issues of uneven distribution. The height of that packed bed is not tall enough for me to achieve a uniform distribution of my fluid throughout that packed bed. Then when I move to the other side of the spectrum, I'm actually able to get relatively easy distribution of my fluid within my particles because I have such a tall packed bed. Unfortunately, as you might imagine, as the height of my packed bed increases, the pressure drop across that packed bed increases. And having a significant loss of pressure of my fluid, right, might not be ideal for my particular scenario. So this ratio between the height of the packed bed and the diameter of the packed bed is a very important parameter when designing your packed bed or fluidized column. Or fluidized bed column, I am going to briefly mention and point out these different types of distributor or distribution plates. I'm not going to spend a bunch of time on this. I'm just going to point out the fact that they exist and there are multiple kinds of distributors. On the following page, what you have is the scenario of going from a packed bed or fixed bed to what we can call smooth fluidization. This is our ideal fluidized bed scenario. As you can see from that particular schematic, the particles are very evenly distributed throughout my fluidized bed, and therefore the gas or the liquid that's flowing through or causing my bed to become fluidized is uniformly distributed within my packing. Let's talk about the one directly to the right of our fixed bed. So again, we're going to imagine a scenario. We have a collection of ratchet rings, and we dump them into the column. They settle, they form some random packing, and then at t equals 0, we open up a valve and begin to flow air into our column. We continuously open that valve, increasing the flow rate of air until we eventually reach a flow rate at which the onset of fluidization begins. That is what we are calling our minimum fluidization. And the velocity at which the fluid is moving to cause minimum fluidization is what is known as the minimum fluidization velocity. And we'll talk about that in a bit more detail in the upcoming pages of the lecture notes. So, crank up the velocity of our air. We eventually begin to make that packed bed start to act like a fluidized bed. That is, the particles are beginning to act less like a collection of solid particles and more like a flowing fluid in my system. I can run into some issues depending on the flow rate of my fluid, the geometry of my column, that is the diameter of my column, as well as the particular packing material itself. Right? In this schematic, they point out two less than ideal scenarios. One is what is referred to as bubbling fluidization. In bubbling fluidization, what you have is an uneven distribution of both your gas and your packing, and it's so uneven that you end up forming these large voids within your packed bed, and hopefully it is relatively obvious that if I examine or compare those two those two fluidized beds, that the one here on the left shows a much more even distribution of both my packing and my fluid within my fluidized bed. If my column happens to be a bit too narrow, based on my particular scenario, I could end up with what is called slugging. And slugging simply means that at some point within my packed bed, a slug of fluid where there is not a high concentration of particles forms within my fluidized bed, and it is sandwiched between two higher concentrations of fluid. So again, essentially creating a slug of fluid within my fluidized bed. Both of these are not ideal. Right? They do not result in an even distribution of fluid. Therefore, they are not serving their main purpose here, which is to help evenly distribute the fluid by increasing its interfacial area between, in this case, the gas and the catalyst part, the packing, I don't want to be specific yet, the packing itself. Right? The point of our packing here is oftentimes, well, I shouldn't say oftentimes, all the time, is to increase that contact area between, we'll take the water and sulfur dioxide example. If I have H2O coming from the top, air plus SO2 coming from the bottom, having those particles I don't want to use that example, because in that case you're actually using a packed bed, not a fluidized bed. So I'm not going to use that example. I think I've made my point here that if I compare, right, these three packed bed, I'm going to get this right, these three fluidized beds, that my fluidized bed here on the left presents the most ideal scenario because I have even distribution of my fluid throughout my fluidized bed. Okay, what applications might I run into in the chemical industry that involve fluidized beds? One of the most common uses of fluidized beds is simply drying, so drying of particles. And the second is catalysis. And specifically, where you'll run into this most often is in the petroleum industry. And for the petroleum industry, this is referred to as catalytic cracking. So, what is catalytic cracking? I'm going to spend a brief second to walk you through the process of catalytic cracking, because again, it is a very, very common process in the petroleum industry. Let me erase all of this. Okay. This is catalytic cracking. Okay. What is catalytic cracking? And what is it used for? So in catalytic cracking, what I'm doing is I'm taking crude oil, which is simply a collection of high molecular weight hydrocarbons, and I'm using a catalyst particle to, in a sense, fractionate or break down that raw crude oil into more usable products like gasoline, propane, right, and other various useful hydrocarbon materials. Okay, in this particular figure, what you have is on the left-hand side, you have what is called a catalytic regenerator. And on the right-hand side at the top, right, it is listed here as a cyclone vessel. And this is simply a reactor. And what occurs in this process is I have my crude oil that feeds in this particular schematic from the right-hand side. That crude oil is typically being fed in around 350 degrees C. For now, we're just going to ignore this particular stream because you don't necessarily have to have what is essentially a recycle stream here. So we're going to imagine this without this recycle stream. And so what happens here is I have crude oil. The crude oil is fed into my catalytic cracking device. It travels upwards. As it travels upwards, what is occurring is I have catalyst particles that are flowing in this direction to meet the incoming crude oil. These catalyst particles, and here let me make sure that I'm very clear about this. In this particular drawing, all of this darker orange, I guess is the color, shaded region, they are catalyst particles. But they are catalyst particles that are fluidized. That is, they are moving more like a fluid than a collection of solid particles. How are they doing that? Well, they're doing that because I'm feeding hot air into the bottom. That hot air is flowing at a velocity that is high enough to cause my catalyst particles to become fluidized. So crude oil feeds in from the right. We'll talk about this a bit more in a second, but I have catalyst particles that are coming from my regenerator. They are meeting with the incoming crude oil, and that combined slurry is fed into your reactor. That reactor is typically operating around 550 degrees C, and we'll say approximately 2 bar. Okay, and so once I reach this temperature of around 550 degrees C, my reactions begin to happen. Those reactions are on the order of seconds, so we're talking about 5 seconds for this reaction to occur. And what ends up happening is that as the reaction occurs on the catalyst surface, a unwanted product begins to form. That product is what is known as catalyst coke. And the easiest way to think about it is that it's similar to soot. So I have this active catalyst particle. It has no coke on it. It flows, meets my crude oil, goes inside my reactor. The reaction occurs, this byproduct of soot then coats my catalyst particle, covering up its surface and making it inactive. Right? Those inactive catalyst particles are now also heavier because they are coated with a different material or an additional material. Therefore, they sink to the bottom of my reactor and they flow back in to my catalytic regenerator. Right? And the catalytic regenerator does exactly what it sounds like it does. It simply regenerates my catalyst. How does it do that? Well, it does that by burning off that catalyst coke that is coating my particle. So the regenerator here is typically operating around 725 degrees C and a pressure of approximately 2.5 bar. And so there is this continuous cycle of spent catalyst falling back into the regenerator, fresh or regenerated catalyst being intersected or intersecting, I should say, with my fresh crude oil that is being fed in, which all then goes back into my reactor, and I end up with this cyclical process of moving spent catalyst to the regenerator, fresh catalyst back into my reactor. Right, so this is one of the most common uses of fluidized beds when it comes to the petroleum industry. Quick side note, this, gasoline used to be made by thermal cracking, but what they found is actually you can create the gasoline more efficiently and with a higher octane rating when done via catalytic cracking as compared to thermal cracking. I believe that's all I want to say about catalytic cracking at the moment, so we'll go back to our fluidized bed lecture. Okay, below or on the rest of this page, what we have here, right, are two different ways to define the size of my catalyst or packed bed particles. Fluidized bed particles, excuse me. So you can imagine I buy some collection of some catalytic nanoparticle. That nanoparticle, or those collection of nanoparticles, has an average size, but within that entire batch there is, of course, some distribution in sizes. And so depending on how we want to define the distribution of those sizes, we can come up with different diameters or representations of our average diameters for our catalyst particles. And so you have things like volume surface mean diameter, arithmetic mean diameter. I'm going to pause a second here, let people finish writing down these two equations. While you're doing that, I'm also going to point out that I am simply bringing this to your attention so that you recognize, if you hear terms like arithmetic mean diameter or volume surface mean diameter, that you understand what those terms represent. Actually, using these equations to calculate a value for the arithmetic mean diameter is not something, that you will have to do for this course. I am again simply pointing these out to you so that you have an understanding or have seen these terminology, or have heard this, I'm going to get this right. I am pointing this out to you just so that you have at least heard of these terms when you leave this class. So there are two here. We're going to move on to the next page where I have my mass mean diameter and my volume mean diameter. Again, just two different ways to represent the average diameter of some collection of particles that I have in my system. Below, I have an example, right, just going through using one of those formulas. In this particular case, I'm asked to calculate the arithmetic mean diameter. And based on this collection of quartz particles, right, based on the exact number of particles that exist within a particular size distribution, I can calculate this arithmetic mean diameter, and I get a value of around 70 microns. Again, let me be explicit here. You will not have to use any of these equations to calculate any value on an exam. I am simply introducing these to you so you have heard of them, you have seen them right before leaving this course. Okay. Now let's discuss in a bit more detail some more useful terminology or equations related to fluidized beds. So what we are going to do here is we are going to derive or simplify equations based on the Ergun equation to calculate my minimum fluidization velocity. My minimum fluidization velocity, as I mentioned earlier, is the velocity at which my bed becomes or starts to become fluidized. If I imagine a particle in my fluidized bed, I can determine, or I can relate the pressure drop across my bed to the weight of that bed and the cross-sectional area of the column. So the pressure drop is equal to the weight of the bed divided by unit area of cross-section. I can use that equation to recast my pressure drop as a function of the height or the length of my bed. That is equal to gravity times 1 minus epsilon, or the void fraction of my packed bed. Here, let's just divide by G sub C to be general, because we are going to have density terms here at the end. So I have gravity multiplied by 1 minus the void fraction, and that multiplied by the density difference between the particle and the fluid. So if I recall my Ergun equation that we just spoke about, at minimum fluidization, this void fraction, my epsilon, becomes epsilon sub m. And my superficial velocity, again, the superficial velocity is the velocity of the fluid as if there were no packing present in the column. That superficial velocity now becomes a minimum fluidization velocity. So I am going to use this equation with the Ergun equation to develop an equation that allows me to calculate the the minimum fluidization velocity of my fluid based on the particle Reynolds number. So, for particle Reynolds numbers less than 1, this oftentimes means very small particles. This is our Stokes flow regime. The minimum fluidization velocity is approximately equal to gravity times the density difference between the particle and the fluid, the sphericity and diameter of the particle squared. All of that is divided by 150 times the viscosity of my fluid, and I multiply that by my epsilon sub m, or void fraction at minimum fluidization. That's to the third power minus 1, divided by 1 minus epsilon sub m. Okay, so all I have done here is I've taken the left term on the right-hand side of my equation. I have gotten rid of the left term on the right-hand side, I've gotten rid of the right term on the right-hand side of the equation because that deals with high particle Reynolds numbers. And everywhere I had a superficial velocity, I inserted a minimum fluidization velocity, and I got rid of my pressure drop by using the equation above. That's for particle Reynolds numbers less than 1. I can have an equation for particle Reynolds numbers greater than 1,000. So the minimum fluidization velocity when I have a particle Reynolds number greater than 1,000, this oftentimes means I have larger particles. This is approximately equal to the sphericity and diameter of my particle times gravity times the density difference between the particle and the fluid multiplied by the void fraction at minimum fluidization cubed divided by 1.75 times the density of my fluid, And all of that is raised to the 1/2 power. I can take these two equations, much like I have for my Ergun equation here, and combine them so that I can calculate a minimum fluidization velocity irrespective of what the particle Reynolds number is. So by combining those two equations, I end up with what I'm calling the full equation, which looks like this. So I have my term for particle Reynolds numbers less than 1. I add the term for particle Reynolds numbers greater than 1,000. And that is all equal to gravity times the density difference between my particle and my fluid. So that full equation will allow you to calculate the minimum fluidization velocity based on the void fraction at minimum fluidization, the density of the fluid, the viscosity of the fluid, as well as the sphericity and diameter of your particle. Or you could think about that the other way. You may be given some minimum fluidization velocity and use that to calculate the void fraction at minimum fluidization. The question then arises of how do we actually calculate or measure this minimum fluidization velocity. And if you move to the next page, what I am showing here is a plot. On the on the y-axis of my plot, I have both pressure drop and bed height. And on the x-axis, I have those two terms as a function of the superficial velocity of my fluid. Okay, so let's do this in different colors since I have that. We'll make bed height blue, pressure drop black. So let's think about it in terms of bed height. What happens here is that at superficial velocity of 0, I have a packed bed or a fixed bed. I begin to increase the superficial velocity of my fluid. I'm measuring the height of my bed. There is some jump in that bed as minimum fluidization starts to occur. And I continue to increase my superficial velocity until I get this linear regime with respect to superficial velocity and bed height. What happens next is once I reach the superficial velocity here at point C, I then start to crank down the velocity of my fluid. As I do that, we'll pick a different color, orange. I start to measure my bed height. That bed height should be consistent with what I measured as I was increasing the superficial velocity. But what you will find is that at the end, when you drop the velocity down to 0, we have now settled to a new bed height. Again, this happens because I have dumped some random packing into my column. When I first dumped it in there, it had a void fraction. I then fluidized my bed. I allowed my bed to then resettle. And when it resettled in a different manner than it did when I first poured them into the column. that point or that break between the curve as I am increasing the velocity and the curve as I am decreasing the velocity is taken as the minimum fluidization velocity. We can do the same thing with the pressure drop. We can measure the pressure drop across that bed, increase the velocity, decrease the velocity. You're going to see some discontinuity in that measurement, and it is at that point where the two curves diverge that I calculate or measure my superficial velocity. Hopefully that makes sense to everyone. Let's keep rolling. So terminal velocity, I'm not going to talk about this at all. You're not going to have to calculate anything related to this on an exam. It's here for you if you want to reference it at any point. But again, I'm not going to focus or spend much time on this at all. Okay. The last thing I want to talk about is how to actually quantify or measure or calculate, I should say, bed expansion. The question I have at the top of the page, how tall does the vessel need to be to hold the particles? Right, you have what's called particle attrition, meaning that you can blow particles out of the top of your column. Once you do that, those particles are no longer useful to you. In most cases, right, you could have a case where you have something like catalytic cracking, where you want that circulation of particles between one vessel and another. Right? But a lot of times, all you're trying to do is fluidize those particles within a single column. And so you want to ask yourself at the end of the day, based on the velocity of my fluid, how far is my packed bed going to expand when it becomes fully fluidized? And is my column tall enough to support that increase in height? I can calculate my new height based on the following formula, which tells me that the length or height of my column is equal to the length or height of my column at minimum fluidization multiplied by 1 minus the void fraction at minimum fluidization divided by 1 minus the void fraction of my expanded or fluidized bed. Next question you might ask yourself is, how do I actually obtain this void fraction of my fluidized bed in the scenario of a particle Reynolds number that is less than 1? So again, we are in Stokes' flow regime. Let me write that properly. I can calculate, and really, let's be honest here, I can estimate that void fraction at my fluidized or expanded bed height based on, this should be, yes, I can estimate the void fraction of my expanded bed based on the part of the Ergun equation that is for small or low particle Reynolds numbers. The issue with this analysis is that it is only valid for low particle Reynolds numbers, because in actuality the Ergun equation that we're utilizing there only applies to fixed beds. So we can use that equation and gain some rough estimate of what the void fraction of our fully fluidized bed looks like. This says also see figure 713. So this figure here is related to the minimum fluidization velocity based on the particle diameter, as well as the density difference between the particle itself and the fluid. And then this dotted line here is our terminal velocity. So the two figures that I'm directing your attention to, or the one figure I'm directing your attention to, so this is actually 713 in the newest edition or 7th edition of the textbook. I pulled this from an old edition online, so just cross that out and make that 713. The following figure allows me to determine or calculate either the void fraction at my expanded bed height based on the height of that expanded bed and the velocity, or vice versa. I have my velocity, I know my void fraction of my expanded bed, but I don't know the height. That, of course, is the less common scenario. Right? More often than not, you're able to measure the velocity of your fluid. You're able to visually measure the height of your expanded bed, and therefore you could use this figure to potentially calculate the void fraction of that expanded bed. And what I'm showing here in figure 713, which again this is from an older textbook, so what figure is this? This is actually figure 715 in your textbook. And we'll come back to that figure here in a second. Because what I want to do now is work through an example problem. So hopefully you can better understand how we might apply some of these equations to fluidized beds. Okay, in the following example problem, we have a bed of ion exchange beads. The height of that bed is 8 feet. And what we're planning on doing is backwashing that bed to remove any dirt that may have gotten on our ion exchange beads. The particles themselves have a density of 1.24 grams per centimeter cubed, and the average size of our particles is 1.1 millimeters. You're told to assume that the viscosity and density of water are 0.01 poise and 1 gram per centimeter cubed. And you're also told to assume that the beads are spherical and that the void fraction at the minimum fluidization is taken as 0.4. So you're given epsilon sub m is equal to 0.4. Part A of the problem asks you to calculate the minimum fluidization velocity based on the information that you are given. So I will start with the Ergun equation. So I have 150 viscosity minimum fluidization velocity divided by sphericity diameter of particle squared 1 minus epsilon sub m divided by epsilon sub m cubed. Now my term for high particle Reynolds numbers, 1.75 times the density of my fluid times the minimum fluidization velocity squared. All of that divided by the sphericity and diameter of my particle, and that is multiplied by 1 over epsilon sub m cubed. All of that, again, is equal to gravity times the density difference between my particle and my fluid. Okay, so let's start plugging in some numbers. we have 150 times 0.01 poise, our minimum fluidization velocity. We're told to assume that we have spheres. We're given the diameter of those spheres. So that would be, no. Yes, that's correct. Because this is going to be in centimeters. So square that. Then we have 0.6 divided by 0.4 cubed plus 1.75. The density of my fluid, I'm told, is 1 gram per centimeter cubed. I have my minimum fluidization velocity squared divided by, again, sphericity is 1, diameter of my particle is 0.11 centimeters. 1 over 0.4 cubed. And all of that is equal to gravity, which I'm going to write in terms of centimeters per second squared. So 980 centimeters per second squared. And the density difference here is 1.24 minus 1. So I end up with 0.24. If I simplify that equation, what I end up with is a quadratic equation. So 1,162 times the minimum fluidization velocity plus 248.6 minimum fluidization velocity squared. All of that equal to 235.2. I can use the quadratic formula. I can plug that into my calculator and solve for the minimum fluidization velocity. And when I do that, I get a value of 0.194 centimeters per second, or 1.94 millimeters per second. That is the velocity of my water at which my bed becomes or starts to become fluidized. Okay, so part A, done. Part B asks what velocity is required to then expand the bed by 25%. We're going to need to make use of our equation. L equals L sub m, 1 minus epsilon sub m divided by 1 minus epsilon. I'm asked to calculate the velocity required for the bed to expand by 25%. And so what I need here is a measure of the epsilon at that 25% expansion. Okay, so based on my minimum fluidization velocity, I can come up with a particle Reynolds number. So let's do that first. So my particle Reynolds number is equal to 0.11 centimeters times 0.194 centimeters per second divided by, multiplied by 124 grams per centimeter cubed divided by 0.01 poise, which is equal to about 2.7. So at 25% expansion, right, we're looking to calculate the velocity that causes our bed to become expanded by 25%. Based on this particle Reynolds number, right, we can calculate or determine this parameter m. So the other equation that you're going to need here that we haven't talked about yet is the following equation, which is the ratio of the void fraction of the bed when it's expanded by 25% divided by the void fraction of the bed at minimum fluidization. All of that raised to this parameter m, and that is equal to the velocity in my expanded bed divided by the minimum fluidization velocity. I get my parameter m from figure 715. So based on my particle Reynolds number of about here, I move upwards to my line and I get an m of around, we'll say 3.9. So let's go back to our problem. This equation now becomes epsilon divided by epsilon sub m raised to the 3.9 power, and all of that is equal to, right, this velocity that we're trying to solve for divided by our divided by our minimum fluidization velocity, which we'll just write in terms of millimeters per second here, so 1.94 millimeters per second. Okay, so in this equation, I know this. This is 0.4. I'm given that. However, I do not know this term, and I do not know that term. However, I can use the above equation to determine what that void fraction is at my 25% bed expansion. The bed is expanded by 25%, so that means that L here is equal to 1.25 times Lm. So I plug that into my equation, do a bit of rearranging, solve for epsilon here, and I get a value of 0.52. So all I've done is I've taken this, I plugged it back into my equation because I know the height of my bed at minimum fluidization. And I know the relationship between the expanded bed and the height of my bed at minimum fluidization. With that, I can calculate this void fraction of my expanded bed. I can take that void fraction, I can plug it right back in to my equation here, and now the only unknown is this velocity that is causing my bed to be expanded by 25%. I solve for that velocity, and I get a value of around 5.4 millimeters per second. Okay, so that 5.4 millimeters per second is the velocity required to expand the bed by 25%. Okay, so that concludes our lecture on fluidized beds. That also officially finishes off our lectures in terms of strictly fluid flow for this course. You saw yesterday I uploaded a video for lecture 18, which was an introduction to heat transfer, specifically an introduction to conductive heat transfer. And so moving forward, we are now going to exclusively talk about heat transfer. But you will see that the idea of fluid flow is going to feed itself into heat transfer when we start talking about convective heat transfer. Okay, so with that, I am going to stop talking. I wish you all a great day. I hope everyone is doing well, staying safe, staying healthy, and I will talk to you again soon.